Swayam Prabha. Digital India. Educated India.
Our aim is to design optimal knowledge base of a fuzzy reasoning tool. Now, what we do is in approach 1, which I have already discussed, the designer based on his own experience of the problem to be modeled, he or she designs the knowledge base, that is the rule base and database of the fuzzy reasoning tool. Now, after that we use one optimizer, say one nature inspired optimization tool like genetic algorithm, to tune its database and rule base. Now, this genetic algorithm through a large number of iterations will try to find out what should be the optimal knowledge base for this fuzzy reasoning tool. Now, supposing that we are going to model a very complicated process, is a real world problem, and it is bit difficult for the designer to determine the knowledge base and the rule base of the fuzzy reasoning tool beforehand. Now, in that case actually we cannot go for approach 1, that is the genetic algorithm based tuning of the knowledge base of fuzzy reasoning tool, and there we will have to go for another approach, and that is your approach 2, that is nothing but automatic design of FLC using a genetic algorithm. Now, here we do not determine the rule base of the fuzzy reasoning tool or fuzzy logic controller beforehand, because we do not have sufficient information of the process to be controlled. And here the whole task of designing the rule base is given to the genetic algorithm. Now, genetic algorithm through a large number of iterations will try to evolve what should be the optimal database and what should be the optimal rule base of the fuzzy reasoning tool, so that it can make the prediction as accurately as possible. Now, this approach, that is approach 2. So, we are going to discuss with the help of one numerical example. The same numerical example which I considered for approach 1. So, I am just going to consider once again. So, our aim is to design and develop the knowledge base of one fuzzy reasoning tool or fuzzy logic controller, whose aim is to model a process having two inputs I 1 and I 2, and it has got only one output, that is O. Now, we have already discussed that 4 linguistic terms are used to represent I 1, I 2 and the output O, and the linguistic terms are like your like very low, low, medium or high, or it could be your say low, medium, high and very high. So, we are going to consider the 4 linguistic term, that is low, medium, high and very high. So, I have got 4 such linguistic terms here for representing I 1, I have got 4 linguistic term for representing I 2. So, I have got 4 multiplied by 4, there are 16 rules, that means 16 possible combination for the input parameters. And once again we are going to use 4 linguistic terms to represent the output, that is we are going to use low, medium, then comes your high and very high. Now, let us see how can you implement this particular approach, that is automatic design of FLC using a genetic algorithm. Now, here what we do is, so there are 4 outputs, 4 linguistic terms for the outputs. So, what we do? So, we try to represent, say if the output is low, that is represented by say 0 0, then medium can be represented by 0 1, high can be represented by 1 0 and very high can be represented by your 1 1. So, to represent the output of a particular rule, so we are going to use in fact 2 bits and there are 16 rule. So, I will have to use 16 multiplied by your, that is your 32 bits to represent what should be the output of this particular the rule. Now, here, so we have got the variables like the way I discussed in the first approach. So, we have got the variables to represent the shape of the membership function distribution for input 1, that is nothing but B 1 if we remember. For I 2 we have got another variable, that is B 2, and for this output we have got another variable, that is nothing but your B 3. So, we have got B 1, B 2 and B 3. So, these 3 real variables, and then we have got 16 rules just to represent the presence or absence of the rules, and we have got 16 multiplied by 2, that is 32 bits to represent what should be the output for the 16 rules. Now, if you see, we have got, we are assigning, so 5 bits to represent B 1, 5 more bits to represent B 2 and 5 more bits to represent B 3. Then there will be 16 bits to represent the 16 rules, like the presence or absence of a rule, and 2 multiplied by 16, that is 32 bits to represent what should be the output for the 16 rules. So, we have got 5 plus 5 plus 5 plus 16 plus 2 into 16. So, total we have got 63 bits. So, the GA string will be 63 bits long, and each particular GA string will carry information of the database and rule base and the output of the rules for this the fuzzy logic controller. Now, our aim is to pass, so one set of inputs like I 1 is equals to 10 and I 2 is 28.0, and so we have got some actually the target output, that is 3.5, and we will try to find out what should be the calculated output, and that particular calculated output will be compared with the target output just to find out the deviation, and this particular deviation we will have to minimize. So, this is actually the problem description. The same numerical example we are going to solve using approach 2. The only thing, the only difference here is in earlier approach, that is approach 1, we have predetermined set of rules, and here we have got the combination of the input parameters, but their corresponding outputs are not known. Now, here actually we are going to use genetic algorithm to find out what should be the output for each of these 16 rules. So, this is actually your this approach to. Now, I am just going to solve this numerical example in details. Now, if you see the population of the solution or the GA strings, so each particular GA string will look like this. So, as I mentioned that, so it has got 63 bits. So, this is nothing but the first GA string. Similarly, we have got second GA string and we have got capital N number of GA string, because the population size is nothing but your capital N, and generally we consider, so might be say n is equals to say 100. So, we have got 100 such GA strings in the population, and these particular GA strings are generated at random using the random number generator. Now, if I concentrate on a particular GA string, for example, the first GA string here. Now, let us see how to determine the output corresponding to this particular the GA string. Now, here, so this shows in fact the first GA string. So, this in fact this is in fact the first GA string. So, the first 5 bits represent the B 1, that is 1, 2, 3, 4, 5. So, 5 bits represent B 1, the next 5 bits represent B 2, and B 3 is represented by the next 5 bits. Now, 16 bits are going to represent actually the presence or absence of the rules, and the output of the rules are represented by. So, these 32 bits, this is 16 multiplied by 2, that is 32 bits. So, one complete GA string is going to represent actually the database and the rule base for this particular the fuzzy logic controller. Now, let us see how to find out the output for a set of inputs. Now, corresponding to this particular 5 bits used to represent B 1, so we can find out what should be their real values, knowing the lower limit and upper limit for this particular the B 1. Now, if you determine the real values for this particular B 1, so we will be getting 3.41 9355. So, this is the real value for B 1, and by following the same principle I can find out the real value for B 2, and that is nothing but 9.193548. Then corresponding to this I can find out the real value for this particular B 3, and that is nothing but 1.370968. And once you have got the real values for this particular B 1, B 2 and B 3. So, now we are in a position to find out what should be the membership function distribution or the modified membership function distribution for this B 1, B 2 and B 3. Now, if you see the modified membership function distribution, so this is actually the modified membership function distribution for I 1, this is for I 2 and this is for the output O. And as we discussed that we have got 4 linguistic term low, medium, high and very high for I 1, I 2 and this particular the output. The only thing is we have optimized what should be the base width for the right angle triangle used to represent low, or the half base width for the isosceles triangle used to represent medium and high and so on. And for simplicity, so we consider the symmetric triangles. So, this is the modified membership function distribution for I 1, modified membership function distribution for I 2 and modified membership function distribution for your the output. Now, actually what we will have to do is we will have to represent or we will have to find out what should be the rule base, and the rule base which is represented by your so this particular the GA string. Now, before that let me just try to say that if I put I 1 equals to 10 and I 2 equals to 28. So, this if I put I 1 equals to 10 here, so I 1 equals to 10 means I am here. So, this particular I 1 can be called your medium with this much of membership function value, and it can be called high with this much of membership function value. Similarly, if I just write here I 2 equals to 28 and corresponding to 28, we can find out the membership function value corresponding to low and membership function value corresponding to this particular your the medium. Now, let us see what happens to the rule base. Now, to find out the rule base corresponding to this particular your the substring, I should say, for example, say these 16 bits will represent the presence and absence of the rule. That means, if I start from here, so one indicates that the first rule will be present, then second, third, fourth will be absent, then the fifth rule will be present and so on. Now, if I just implement, so very easily you can find out what are the rules to be there in the rule base. Now, if I consider that this first rule is present and what should be its output, so that is decided by these 2 bits. Now, this is 0 0. Now, if it is 0 0, so this is nothing but is your so this is nothing but the first option, that is your that is the low. So, the first option that is going to be indicated by this 0 0. So, this is nothing but the low. So, if the first rule is present, so its output will be the low. Now, if I just see this, so on this particular table, so I can find out the according to that particular substring. So, the rules which are present, which are found to be present are as follows, like if I 1 is low and I 2 is low, then the output is low. So, this particular rule is present, but the second rule is absent, the third rule is absent, the fourth rule is absent, then the fifth rule is present, which states if I 1 is medium and I 2 is low, then the output is medium. Then sixth is absent, seventh is present, eighth is absent, the ninth is present, 10th is absent, and so on. Now, as I told that this particular I 1 which is equal to 10.0, it can be called either medium or it could be high. Similarly, the I 2 which is equal to 28.0 can be called either low or it can be called medium. So, there is a maximum of 4 fired rules, and let us see out of those 4 fired rules which one or which 2 or which 3 or whether all 4 are present or not. Now, let me try to find out whether the first combination is present or not. So, if I 1 is medium, so I am here, if I 1 is medium and I 2 is low, so I 2 is low, then output is actually your the medium. So, this particular the rule is present. So, this is present. Next is if I 1 is medium and I 2 is medium, the rule is absent here. The next is if I 1 is H, so I am here and I 2 is low, that means I am here. So, this particular rule is present whose output is actually high. The next is if I 1 is H, so I am here and I 2 is M, so I am here. So, that particular rule is absent. So, out of the 4 maximum rules, only 2 are found to be present here, and the rules are as follows, like if I 1 is medium. So, if I 1 is medium and your I 2 is low, then the output O is nothing but output is the medium. So, this is one present fired rule, and another present fired rule is if I 1 is say high. So, this one and I 2 is low, then the output O is nothing but is high. So, out of these 4, only these 2 rules are found to be present here. Now, you will have to find out what should be the output corresponding to these 2 fired rules, and then I will have to combine just to find out what should be the combined output or the combined control action. Now, let us see how to find out. Now, corresponding to the first fired rule, that is if I 1 is medium and I 2 is low, the output is medium. So, what you can do is we can find out what should be the fuzzified output, and corresponding to the second rule, once again I can find out what should be the fuzzified output, and then we combine, then we will be getting the fuzzified output for the combined control action considering these 2 rules. And once we have got it, now we can use the center of sums method of defuzzification, and if I use it, so there is a possibility that you will be able to find out what should be the crisp output, and that is coming to be equal to 4.056452. Now, this is the calculated output corresponding to the inputs like I 1 is 10 and your I 2 is nothing but 28.0. Now, this is actually the output, but the target output is nothing but is your 3.5. So, there is some deviation, and here, so this particular deviation, that is 3.5 minus 4.056452. So, this is nothing but a negative value, and that is why we use the mod value just to make it positive. That means So, out of all the training scenarios which we have, so if I pass the first training scenario, so I am getting this particular your deviation. Now, by following the same procedure, I am just going to pass the second training scenario, third training scenario up to the tth training scenario. Now, if I pass all the training scenarios, then I will be getting actually your the different deviation values. Now, corresponding to the first training scenario, say the deviation is denoted by say d 1, corresponding to the second training scenario, supposing that the deviation is denoted by say d 2, and corresponding to the tth training scenario, supposing that the deviation is represented by d t. Now, what we do is we try to find out the average deviation, and that is nothing but the sum of all d values divided by the number of training scenarios, that is nothing but t. So, I can find out what should be this average deviation, that is d bar, and once you have got this average deviation, now this average deviation is nothing but the fitness for the first GA string. So, I should be able to find out what should be the fitness for the first GA string, that is your F 1, and by following the same procedure I can find out the fitness for the second GA string, and we try to find out following the same procedure the fitness for the other GA string, and for the nth GA string the fitness is denoted by F n. Now, we take the help of the GA operators like the reproduction, crossover and mutation, and GA through a large number of iteration we will try to find out what should be the optimal database and what should be the optimal rule base for this fuzzy reasoning tool. And once you have got this optimal database and rule base, so what you can do is, now this optimal fuzzy logic controller you can use for your for online application. That means, we can pass some test scenario and we can find out what should be the output for a set of inputs. Now, if you optimize or if you try to evolve the knowledge base, that is the rule base and database, particularly the rule base of a fuzzy logic controller, by following this particular the method which I have already discussed, there is a possibility that there will be some redundant rules in the rule base. Now, redundant rule means, like, let me try to explain. Supposing that I have started with say 16 rules. Now, I have started with 16 rules. Now, if I just do this GA based tuning which I have already discussed, that automatic design of fuzzy logic controller using the genetic algorithm, there is a possibility, say I will be getting say 9 good rules out of these particular the 16. Now, these 9 I will be getting if I just do the GA based tuning only once. Okay. Now, if I do the same GA based tuning once again, so there is a possibility that from 9 it may select only 6 rule or the 7th rule from the out of this particular the 9. So, we will be getting the further tuned rule base. Now, if I follow this particular principle, that means there are some redundant rules, okay, and those redundant rules in fact we will have to identify. Now, to identify the redundant rules, so what we do is we introduced one technique, like we calculated what we mean by importance factor. Now, this importance factor that is denoted by say I f to find out. So, what we do is we try to find out what is the probability of occurrence of the different rules during the training. That means, a particular rule how many times it has been fired during the training scenarios or during the training, and we try to find out what is the probability of occurrence of all the possible rules during the training, and moreover we try to find out what should be the worth of a particular rule. Now, this worth is decided for the set of inputs, what is the output. Now, out of these 16 rules, say the importance of all the 16 rules may not be equally good. Now, what we do is we try to represent the importance of each of these particular rule in a scale of say 0 to 1, and if I get the worth of a particular rule and the probability of occurrence. So, both the things are going to lie between 0 and 1. So, I will be getting some value lying between 0 and 1, and if you multiply them. So, I will be getting another value which is once again will be lying between 0 and 1. Now, if that particular value, that is nothing but the importance factor. Now, if this importance factor is found to be say less than some threshold value. So, some threshold value, predetermined threshold value. So, if it is found to be less than that, that means that rule is not very good, and that can be declared as a redundant rule. So, this is the way actually we declare the redundant rules. But if you just go on tuning, so this particular the rule base of the fuzzy logic controller. So, there is a possibility that it will give rise only a very weak or a very optimized rule based sort of thing, and there could be a few test scenarios. Now, if I pass those test scenarios, so there is a possibility that not even a single rule is going to be fired, and that is actually the problem of no firing. Now, by no firing, in fact, we mean a situation whenever we are passing say one set of training, one set of inputs, but it is not going to actually the trigger any of the rules, and none of the rules is going to be fired. So, we cannot find out actually output for these set of inputs. So, that particular situation is nothing but actually the no firing situation. So, our aim is to reduce the redundant rules, but at the same time we should take care that there should not be any such no firing or weak firing. Now, this is the way actually we can optimize the fuzzy reasoning tool, and now I am just going to discuss in short like how to carry out optimization for the fuzzy clustering. Now, we have already discussed that our aim is to determine the clusters which are very distinct, and the clusters should be very compact, and at the same time the number of outliers should be as minimum as possible, and in fact ideally we want that there should not be any such outliers. Now, if I just formulate this particular problem as a maximization problem, so I can formulate like this. So, maximize say f is nothing but say W 1 multiplied by the distinctness, say this is denoted by D, plus W 2 the weighting factor multiplied by the compactness, say this is denoted by C, plus. So, our aim is to minimize outlier. So, I can write down W 3 multiplied by 1 divided by say O prime, which indicates your outliers. So, our aim is to maximize so this particular objective function, and once again we can take the help of your so this type of say genetic algorithm, and genetic algorithm is going to encode. So, the values for this D, then comes your C, and this say your 1 divided by O prime, that is your outliers, and your the sum of all the W values should be equal to your 1.0. So, all such values, so we can actually we can find out, and we can find out what should be the distinctness, what should be the compactness, and what should be the number of outliers. So, these are the things which we will have to find out, but what should be the design variables? The design variables or the performance of a fuzzy clustering tool. So, fuzzy Siemens clustering depends on the number of clusters to be made, then comes your the initial matrix of your membership values and the level of cluster fuzziness. So, all such things are the design parameters for this FCM, that is your fuzzy C-means clustering, and we can use some GST to represent the design variables, and this should be your objective function, and our aim is to maximize. So, this particular the objective function, and GA will try to find out through a large number of iterations, like what should be the number of clusters to be made, what should be the matrix for the membership values, and what should be the level of cluster fuzziness, so that this particular condition gets fulfilled, and it will try to find out. So, the optimal clustering using the fuzzy C-means clustering. Now, next we try to see another method of clustering which we have used, that is entropy based fuzzy clustering, and if I want to carry out the similar type of optimization, where our aim is to maximize the distinctness, to maximize your the compactness, and to minimize the number of outliers. So, we can use the same principle for this entropy based fuzzy clustering also, keeping the same objective function. Now, here the design variables will be your, so this particular alpha, beta and gamma, this I have already discussed. Now, alpha actually indicates the relationship between the Euclidean distance and similarity, and beta represents the threshold value of similarity, and gamma indicates actually your the outliers. Now, in the GA string, so if I consider say a particular GA string something like this, say this is one say GA string. So, if I consider, so it can represent the value of alpha, then comes your beta, and then comes your gamma, and we can generate a population of solution. Now, corresponding to this alpha, beta and gamma, so it will carry out some sort of fuzzy clustering, and we will be getting the quality of clusters in terms of the distinctness, in terms of the compactness, and we can also find out whether there is any such outliers or not. And GA through a large number of iterations, we will try to find out that values of alpha, beta and gamma are corresponding to a particular say the data sets, so that it can ensure the optimal clusters. Now, this is the way actually we can carry out some sort of optimization. If I want to optimize the performance of fuzzy logic controller and performance of your fuzzy clustering tools. Now, this is actually the reference based on which so we carried out this discussion, that is the soft computing fundamentals and applications by D.K. Pratyar. So, this is the textbook for this course. So, you can refer to this, and here I just want to summarize whatever we have discussed in this particular lecture. Now, at the beginning we gave a brief introduction to the nature inspired optimization tools, particularly the genetic algorithm. We spent some time on optimization of fuzzy reasoning tool or fuzzy logic controller, like how to find out the optimal database, optimal rule base for the fuzzy logic controller. So, that we discussed in details, and we solved some numerical examples also. Now, next in fact we concentrated on how to optimize the clustering algorithms like fuzzy C-means algorithm or entropy based algorithm, so that it can ensure the optimal clusters in terms of compactness, in terms of distinctness, and there should not be any such outliers. Thank you.